Good morning, dear students. My name is Ferhan Mazher, and today is the 2nd of May 2022. Right now, I am with the 11th Cambridge class, and the subject we are studying is Cambridge Olevels Mathematics, Syllabus D. The code of the subject is 4024. In this session, in this video, we are going to learn the basic concepts of the angle properties of the circles. And the chapter for practice which we use is chapter number 13 from the D3, New Syllabus Mathematics 7th edition. That chapter is about the circle, the angle properties of the circles. So let's today's lecture. So the first thing coming up on your screen. So these are the angle properties. For example, if you have a chord, and what is the chord? Chord is a line which joins 2 points of the circle. For example, AB is a chord, and this is the center of the circle. We named it as O, and OX is the line segment coming from the center onto the chord AB. So if this line segment from the center makes 90-degree angle with the chord, or in other words, you can say the OX is perpendicular to the AB, then the chord will be bisected. It means that the chord will be divided into 2 equal parts. So the AX and the BX, they will be equal to each other. Here is another example. And in this example, you can see that here we have a CD is a chord, and O is the center, and OY is the line segment from the center onto the chord. And if this angle OYC is 90-degree, then this chord will be divided into 2 equal parts. And this Y will bisect this chord. So this CY will be equals to the DY length. So the chord will be bisected into 2 equal parts. Here is another example of the same property. For example, FE is a chord. Chord is a line in which you join 2 points on the circumference with each other. And OZ is the line segment coming from the center to the chord. And if this angle OZF or the OZE is 90-degree, if the OZ is perpendicular to the FE, then the chord will be bisected. The chord will be bisected means that there will be the chord will be divided into 2 equal parts. So the FZ and the EZ, they both will be equal to each other. So if a line segment from the center makes 90-degree angle with the chord will be bisected by that line segment. Okay, so that's the first property in our syllabus in DMaths D3, and here we go. So here we have another property, and it says that if a chord is bisected by a line segment coming from the center, then that line segment will make 90-degree angle with the chord. So for example, if this is AB is a chord and OX is a line segment coming from the center, then if this divides this chord into 2 equal parts, if it bisects this chord, the angle between the chord and this line segment will be 100% 90-degree. So if the AX is equals to BX, then the AXO angle will be 90-degree. So here we have a chord CD, and this chord here OY is the line segment coming from the center to this chord. And what happened here, that the OY has bisected this chord. It has divided this into 2 equal parts. Then the angle between the chord and that line segment will be 100% 90-degree. This will be 90. So if the chord is bisected, means CY is equal to DY, then the CYO angle will be 90. Here is a third example on the same concept. So if the chord is bisected, for example, this is chord FE, and from the center, a line segment came OZ to the chord, and that divided that chord into 2 equal parts. So FZ is equals to ZE or EZ. So then the angle between the chord and that line segment will be 90 degree. It will be right angle. So the OZF or FZO, you can say, it will be 90. This angle will be 90. This angle will be 90 degree. So that's the first property in our syllabus. Okay, now if you have two chords and we can find the distance of a chord from the center, the perpendicular distance of the chord from the center. If two chords are parallel, then there can be two situations. When the two chords are parallel to each other, either both the chords are on the same side of the center or both the chords are opposite to the center. So, for example, here you can see I have chord AB and the CD, and I suppose that they are parallel to each other. So, but I have shown that they are on the opposite sides of this to the center. So the distance between them, for example, the distance of the AB chord from the center, and I mean the perpendicular distance from the center, that's A, and the perpendicular distance of the CD chord from the center is B. Then the distance between both the chords from each other will be A plus B. Here we have another example, and it's the same example, but this time the AB chord and the CD chord, which are parallel to each other, they are on the same side of the center. So, for example, if the distance of the AB, the perpendicular distance of the AB from the center is A, and the CD's distance from the center is B, then the distance between the two chords will be A minus B. It's a famous question. Okay, here we have two chords, A, B, and C, D, and they are parallel to each other. They are on the opposite side to the center, and they are parallel to each other. So they are the distance of the AB from the center is X, and the distance of the CD from the center is Y. So the distance between them will be X plus Y. And because this is, because here it has been divided into equal parts, so this angle will be 90. Suppose this portion is A, this portion, this length is A. And here again, the line from the center has divided into two equal parts. So this is B, this is Y, this is R, this is also radius, this is A, this is X. So you can apply Pythagoras here. So the R square, if you apply Pythagoras here, it will be R square equals to A square plus X square. If you apply Pythagoras here, it will be R square equals to Y square plus B square. So hopefully you little understand. Here we have a chord. So we have to learn a terminology, and the term is the angle subtended by the chord at the center, or the angle subtended by the chord at the center. So for example, if you have a chord here, for example, you have a chord AB, and you join its point A with the center, you join its point B with the center, the angle between the OA and the OB, that's theta. So this is known as the angle subtended by the chord at the center. For example, here I have a chord CD, and I join its and C with the center of the circle O, and I join the D with the center of the circle OD. With this line is OD, this is OC. So the angle between these two lines will be the angle subtended by the chord at the center, and suppose that's theta. Here you have another example. So for example, this is a chord, its name is EF. If you join it and E with the center O, and you join F with the O, so the angle between the OE and the OF will be theta. So, and this is known as the angle subtended by the chord at the center. So here we have, so for example, here you have a chord AB, you join A with the center, you join B with the center. So this is radius, this one is radius. So the angle between them is theta. So theta is the angle subtended by at the center by a chord. And another important thing is that this is a triangle, and the two sides of this triangle, they are equal to each other. So it's an isotriangle. Here you can see, here we have a chord AB, and I've joined it with the center O, and joined the B with the center O. So a triangle will be formed, AOB. So the angle here, this is theta, this is the angle subtended by the chord at the center. And because the OA is equal to radius and the OB is equal to the radius, so this is an isotriangle. And you know, in isotriangle, these two angles, which are opposite to equal sides, they are known as the base angles, then they will be equal to each other. For example, here I have explained it further. For example, this is a chord AB, and you have joined it with the center. You have joined A with the center, joined B with the center. So OAB is a triangle. So this OA is radius, OB is also radius, and the angle at the center is theta. So this is an isotriangle. So these two angles, at angle OAB and the angle OBA, they will be in the base angles. They will be equal to each other because it's an isotriangle. So I'm named this as alpha, and this is also alpha. So the theta plus alpha will be equal to 180. The reason is this is a isotriangle. It's a very important property, and you should always be able to recognize this. For example, here another example that we have a chord CD. I join the C end of the chord with the center O and the end of the chord D with the center O. So the OC and the OD, they both are equal to each other because they both are equal to the radius of the circle. So the COD will be an isotriangle. So if this angle is theta, that's the angle subtended by the chord at the center. And this is alpha, this will be also alpha. So the theta plus alpha will be equals to 180 because it's an isotriangle. So here we have a very special property. For example, here we have a chord, and it's AB chord, and I join A with the center O, I join B with the center O, and I join A with the point on the circumference C, and I join B with the point on the circumference at that point C, the same point. So the angle here, this angle will be the angle subtended by the chord at the circumference. And the angle here is the angle subtended by the chord at the center. So these are two terms. So angle subtended by the chord at the center and the angle subtended by the chord at the circumference. And you should be able to understand them. So this angle at the circumference, and this is the angle at the center. The angle at the center will be always 2 times the angle at the circumference. So the angle subtended at the center is equals to 2 times the angle at the circumference. So let me show you here. For example, this chord AB. You join the A with the center, you join B with the center. You join A with a point on the circumference, and you join B with the same point on the circumference. So this angle here is the angle subtended at the circumference by the chord, and this angle here is the angle subtended by the chord at the center. So the angle subtended by the chord at the center is 2 times the angle subtended at the circumference. So if this is theta, if this is phi, this will be 2 phi. If this is 20, this angle here will be 40. If this is 30, this will be 60. If it is 80, this will be 160. Here is another example on the same concept. For example, the CD is a chord, and you join the C with the center, you join D with the center. So this is the angle subtended by the chord at the center. You join C with the point on the circumference, and you join D with the same point on the circumference. So this is the angle subtended by the chord at the circumference. So the angle subtended at the center is 2 times the angle subtended at the circumference by the chord. So if this angle is x, this angle will be 2x. If this angle will be 10, this angle will be 20. If this angle is 40, this angle will be half of that. It will be 20. I hope you understand that the angle at the center is equal to 2 times angle at the circumference. Okay, so here we have another property, very important property. For example, if you have a diameter, for example, AB is the diameter. and you join the ends of the diameter with a point on the circumference. For example, you join A with the X and the B with the same point, X. Important thing is this point is on the circumference. The angle subtended by the diameter at the circumference will be 90 degrees. This property is called right angle in the semicircle. For example, a same property, and I will try to explain it again. For example, CD is diameter. Why it is diameter? Because it is passing from the center, and C and D are the 2 points on the circumference. And if I join the C with the point on the circumference and D with the point on the circumference, so this angle formed at the circumference by this diameter will be of the 90 degree. We call this right angle in the semicircle. Here is another example on the same property. And for example, EF is a diameter. Diameter is a line segment which joins 2 points of the circumference, and it passes from the center. And if I join the E end of the diameter with this point on the circumference and F with the same point on the circumference, then the angle between these EZ and the FZ will be of 90 degrees. This is called a right angle in the semicircle. I hope you understand. So here we go to the next property. And for example, if I have a chord, and you can see here we have a circle, this is the center, here is a chord AB. So whenever I draw a chord AB, for example, and that chord divides the circle into 2 portions. Each portion is known as a segment. So this shaded portion is a segment, and this white whole area is also a segment. So if I join the ends of a chord with the points on the circumference, on the multiple points of the circumference, B joined with the C, A also joined with the C, B joined with the D, and the A also joined with the D, B joined with the E, and the A also joined with the E. The important thing is that the C, D, and E, they all are on the same segment. So the angle here formed here, and the angle formed here, and the angle formed there, they will be equals to each other. This is called the angles in the same segment. So the angle ACB is equals to the angle ADB equals to the angle AEB. So let's practice more. So here you can see we have here we have HG, a chord, and this has divided the circle into 2 segments. So this shaded one is a segment as a minor segment. This one is a bigger major segment. If I join the H and the G, which are the ends of the chord, with the multiple points on the circumference in the same segment, but these points are in the same segment, they are in this white segment. So if I join H with the K and the G with the K, so a certain angle is formed here. If I join H with the J and the G with the J, a certain angle is formed here. H with the I and the G with the I, and this angle is formed here. The important thing is that all these 3 points, they are in this major segment. They are in the same segment. So these 3 shaded angles will also be equal to each other. This is called angles in the same segment. So if this one is 30, this will be 30, this will be also 30. So here another example, LM is a chord. So in this circle, LM is a chord. So I have joined the L and the M with the point on the circumference P. I've joined L and M with the point on the circumference, and that point is O. L and M has been joined with the point on the circumference N. The important thing about the P and O and N is they are in the same segment. So this angle, and this angle, they will be equal to each other, and this is called the angles in the same segment. So if this angle is 50, this will be also 50. This angle will be also 50. Angles in the same segment. Now, here we have another property. For example, here is a chord AC. So now clearly you have two segments, and this shaded segment and this white segment. This is the major, this is the minor segment. So if I join the ends of this chord with a point on the minor segment, for example, this point B, which is on the circumference, and I join the ends of the chord A and C with the point D, which is on the opposite segment, the other segment. So, so the angle, this angle and this angle, which are both are the angles subtended by that chord AC on the circumference. But the important thing is that both these angles are in the opposite segment, so their sum will be 180. So the angle ABC and the angle ADC, they will be supplementary to each other. Their sum will be 180. So the angle ABC plus the angle ADC will be equals to 180. We call it angles in the opposite segment are supplementary. Okay, here is another example on the same property. For example, EG is a chord, and you joined the ends of this chord with a point in the on the circumference in the minor segment and a point on the circumference in the major segment. So this AF point is in this segment on the circumference, and H point is in this segment on the circumference. So this angle and this angle, they both are the angles subtended by the chord EG on the circumference, but they both are in the opposite segments. So their sum will be 180. They will be supplementary to each other. For example, this angle, the name of the angle EFG plus the angle EHG will be equals to 180. The angles in the opposite segment are supplementary. Here is the third example on the same property. For example, IK is a chord. And when you draw a chord, obviously the circle is divided into two segments. This shaded one is a minor segment, and that white portion is a major segment. So this one is a major segment, this one is a minor segment. So you join the ends of the chord with the two different points on the circumference. One is in the minor, on the circumference in the minor segment, and the other is on the circumference in the major segment. So when this angle and this angle is the angle subtended by the chord at the circumference, but both of them are angles subtended by the chord, the same chord at the circumference, but they are in the opposite segment. So their sum will be 180. So they will be supplementary to each other. So the angle ILK plus the IJK equals to 180. So because they are supplementary to each other, angles in the opposite segment are supplementary. Okay, so here this is the same property, but with a little different angle. Here you see we have a quadrilateral, and the name of the quadrilateral is ABCD. And the important thing about this quadrilateral, first of all, what is a quadrilateral? Quadrilateral is a figure who has four sides, who has four vertices, a closed figure. So this quadrilateral has four vertices, and all of them are on the circumference. It's an important property. We have a quadrilateral whose four vertices are on the circumference. So this is called a cyclic or cyclic quadrilateral. It's a cyclic or a cyclic quadrilateral. So what we will do, for example, here, the diagonally, the angles which are in the opposite corners diagonally, they will be supplementary to each other. So the angle BAD and the BCD, they will be supplementary to each other. and the angle ABC and the angle ABC, these two angles, they will be supplementary to each other. So this is called the cyclic quadrilateral. So let's do another example, and here we go. Here you can see on your screen, quadrilateral is shown EGHF, and this quadrilateral is called cyclic or cyclic quadrilateral. The reason is its four vertices are on the circumference, and so the angle E and the angle H, they are diagonally opposite to each other. So their sum will be 180. The angle G and the angle F, their sum will be 180. We call this property angles in the opposite segment are supplementary. So angle FEG plus GHF equals to 180. Angle EGH plus angle EFH is equals to 180. Here we have another example. Angles. Here we have a cyclic quadrilateral, JILK. It's a quadrilateral, its four vertices are on the circumference of the circle. So the corners, the vertices which are diagonally opposite to each other, for example, I and K, their angle sum, the sum of their angles will be 180. J and L, their sum will be 180. So you can say, because they are the angles in the opposite segment, or you can say cyclic quadrilateral, or the actual name is angles in the opposite segment are supplementary. So here we have the angle properties of circle, and here we have a tangent. This is AB is a tangent, and O is the center. Tangent is a line which makes which touch the circle at only one point. That is known as the tangent, and this is called the point of tangency. So AB is a tangent, X is the point of tangency, where that's the tangent touch the circle. So the angle between the tangent and the radius at the point of tangency is 90 degree. So tangent is perpendicular to the radius. So AXO angle is 90, BXO angle is 90. Here is another example. This DC is a tangent. It touched the circle only at the point Y. This point Y is the point of tangency. So this is the radius at the point of tangency. The radius and the tangent at the point of tangency, they make 90 degree angle with each other. So the AYC angle is 90, and the OYC and the OYD will be 90 degree. Here is another example. This is a tangent, and Z is the point of tangency, EF is the tangent. So OZ is the radius, they makes 90 degree angle with each other. The radius and the tangent at the point of tangency, they are perpendicular to each other. So the OZ is 90, the OZF is 90. Here we have angle, a tangent, and the point of tangency been joined with the O center, and this point B has also been joined with the center. So it will make a right angle triangle, because this angle is 90. So this is a right angle triangle. You can apply Pythagoras. So the OB whole square will be equals to OA square plus AB square. Here is another example. This is a tangent. The PR is a tangent. Q is the point of tangency. This is a radius at the point of tangency. So they makes 90 degree angle with each other. If I join P with the O, it will be a right angle triangle. So you can apply Pythagoras. So the OP square will be equals to the OQ square plus the PQ square. So here you see this SU is the tangent, and if you join the U with the O, so this will be a right angle triangle. So you can apply Pythagoras here. So TU square and plus the OT square will be equals to the OU square. If you have two tangents coming from the same external point to the same circle, both the tangents will be equal in length. So AT and the BT, they will be equal in length. Here is another example. T is an external point. This is a circle. So two tangents are coming, TD and the TC, and both these tangents are coming from the same external point to the same circle. So both the tangents will be equal in length. So the TC equals to TD. Here is a good example. We have drawn up external point P. Its tangents are PC and the PD. Here we have an external point T. Its tangents are TA and the TB. They are coming from this external point. This tangent and this tangent will be equal to each other. This tangent and this tangent will be equal in length to each other. So if you join, here we have external point, its tangent is AT and the ATB. And if you join the external point with the center, this dotted line will bisect the angle here and bisect the angle here. So this angle and this angle will be equal to each other. This angle and this angle will be equal to each other. Another example, external point is G. From the same external point, two tangents came. I joined the point of tangency with the center. So if I join O with the point, the external point, this will be bisect this angle, alpha alpha. It will also bisect angle at the center, so beta and beta. Here you can see external point is H, and I have joined it with the O, and this tangent and this tangent equal length. This dotted line will bisect the angle here, and it will bisect the angle. It will divide this angle into two equal parts. This angle is also divided into two equal parts. So here, if this angle is 2 beta, this angle will be 360 minus 2 beta. The angle at this portion will be half of this angle. So here is another example. This is the external point. These are the two tangents. They are equal in length. If this is alpha and this is 90-90 and this is beta angle, their sum will be 360. Their sum will be 360. The angle at the circumference will be half of this angle. If this is angle alpha, this is A and B where point of tangencies. This is the external point from where the tangents are coming. If you join A and B with each other, because this and this, they are equal in length. These two tangents are equal in length. So, it will be isotriangle. This will be an isotriangle. So if this is alpha, this will be beta, this will be beta. This is called, if you have a tangent and you have a triangle whose one point is at the point of tangency, and the other two are on the circumference. Its vertices are on the circumference. So the angle formed between the side of this triangle and the tangent, it will be equal to this angle. The angle formed between the tangent and the side of this triangle, this angle will be equal to this angle. This is called angles in the alternate segments. Let me reduce the size so you can see. This is called the angles in the alternate segments. Here's another good example. This is the tangent. This is the point of tangency. Here we have a triangle whose one vertex is at the point of tangency, and the other two vertices are on the circumference. So the angle between this tangent and this side of the triangle will be equal to this opposite angle. So they will be equal to each other. And the angle between the side of this triangle and the tangent, this angle will be equal to this internal angle. So they are known as the angles in the alternate segments. And here we have, if you have two chords and they are equal in length, they will subtend the same angle at the circumference. If you have two equal chords and if you have two equal chords, they will subtend same angle at the circumference. These are two equal chords. So they will have the same angle. This chord at the circumference has alpha angle. This chord equal to this chord. So its angle at the circumference will be also the same. These two chords are equal. So they will subtend same angle at the center. So equal chords subtend equal angle at the center. Equal chords subtends equal angle at the circumference. So my dear students, I hope that this video will help you to to understand the properties of the angle properties of the circle, and you will be able to do question. Whenever you do this question, it always requires common sense and a lot of practice. So I hope it will help you. So if you like it, please share this video and like my video and share my video, and also subscribe my channel. It's a blessing for me to teach you online. Thank you very much. Have a good day. God bless you all.